Hello, everyone. Today we're going to talk about 8.3 confidence intervals for means. So as you can see, we're still constructing the interval using the same general format, statistic plus or minus critical value times SD of statistic. And then this right here, this is still our margin of error. It just is going to look a little bit different working with means and proportions. So to get started, we're going to go ahead and go through the conditions. I'm going to put them up there. Go ahead and jot them down on your notes. Okay, go ahead and jot these down. Similar as last time, random, 10% and normality. The only change to this is that for normality, we're going to talk about this a little bit more. Sometimes we are given just data. So to check for normality, we're going to be using the graph of the sample. So looking at like a histogram or a box plot. And then we'll follow up with that in a little bit. But normality has a few different ways that it can be checked for means. So we're going to go ahead and move on to the next part on here. Very similarly to proportions, if a parameter is unknown, we're going to be building a confidence interval. Since we don't know population standard deviation, we're going to have to substitute in our sample standard deviation. This is called the standard error. Okay. And the way that you calculate it is very similar to what's already on here. Except you're going to be using sample standard deviation instead of population. So standard error of X bar, not P hat anymore, is equal to S of X over square root of N. And if you need to make a note, S of X is sample standard deviation. So if you need to make a note of that, definitely be sure you do that. So under that, it says when population standard deviation is unknown, we must use the T distribution instead of the standard normal Z distribution. So up until now, we've only been looking at the standard normal distribution, which is the Z, right? The normal curve. That's all we've looked at. There are actually other distributions based on different types of models and different information. So you guys are used to this statistic right here, calculating a Z score for something. In our new distribution, since we don't know what this value of the population standard deviation is, we have to use the sample. That's when we use the T distribution. So if you look at this, a few different things, notice how there's more in the tails of the T distribution than there is in the normal. If you guys think about like standard deviation away, that means like there's more data in those tails, like beyond the second and beyond the third. Another important factor of the T distribution is that it's different for every single sample size. So no matter, depending on the sample size, this distribution right here will change. So if your sample size is 10 versus 15, it's a different distribution. Whereas the normal distribution doesn't change, right? It still has that same properties, the empirical rule, all of those things. The T distribution does change. Another important piece is that sample size contributes to what's called the degrees of freedom, okay? And if we look at the next page, the degrees of freedom is just this, defines what T distribution that you're using. So here's a picture on your next page. And if you look here, there's 3 different distributions shown on this curve. The first one is a T distribution with degrees of freedom of 2. The second is one with 9. And the third is the standard normal. So the third one, the purple one, that's the one that we are used to, that we've been working with, okay? So that one is not new to us. What is new are the other ones. And then if you look, degrees of freedom are just defined by the sample size -1. So when we say that we have degrees of freedom of 2, that means our sample size is actually 3. If it's 9, our sample size is actually 10. But the one thing I want you to pay attention to as you look at these, notice the red curve, which is the 2, which is this one right here and this one. There's more in that tail than there is in the 9 and then there is in the normal. So in the T distribution, as your degrees of freedom increases, the distribution itself gets closer and closer to the standard normal. So that's written down here as well. As the degrees of freedom go up, the T curve approaches the standard normal curve even more closely. So as you can see, even 9 is getting closer. If you do 10, 20, 30, that's getting closer to the normal distribution. And eventually it'll be like approximately the same. But the T distribution depends on that sample size. So that's one key takeaway of this lesson as well. is introducing to a new distribution, which is the t distribution. Now, it also has its own table, which is given to you in your folder today and attached with this video. So we are going to go ahead and first talk about critical values. So you guys are used to Z star already. Now we're going to actually look at something called T star. So I'll let you guys pull up that table. And the way that this works is you need a few things first. You have to identify your degrees of freedom. So remember that that's sample size minus 1, sorry, degrees of freedom, DF, equals 12 minus 1. So the degrees of freedom in this case is equal to 11. So again, that just helps us figure out which of the T distributions we are looking at. And it's a little more spread out in the tails, not as close. So the other thing you need to look at is the upper tail probability. So think back to our confidence intervals. If we have 95% in the middle, regardless of where that is on the distribution, you would still have 2.5% on each tail. So 0.025, 0.025. So the other thing that you need is if you look at the T table, it always gives it to you in terms of the right tail probability. So we're looking at 0.025. So right here, looking at degrees of freedom is 11, and my upper tail probability 0.025. So then the value that we would be looking at is right here, 2.201. So that means that our T star would be 2.201. Critical value for T. Okay. We're going to go over this next one just briefly together. So this next one says a random sample of 48 observations. So if you're looking at the table right now, you will notice on there, first you have to think about degrees of freedom. So this would be 48 minus 1. So my degrees of freedom is equal to 47. So you'll notice that there's no 47 on there for degrees of freedom. So we're going to have to go to a more conservative value. We're going to use 40 instead of 50 because we don't know it's quite 50, but we're going to kind of round down. So that will always be the case. You're not going to round to like the nearest 10. Go ahead and always round down. So we're going to use DF of 40. And so if you look at your table and you look at 90% and what's in the tail. So if you had 90% in your middle, in each tail, you're going to have 5%. So that's your upper tail probability. The T value associated with that, the critical T value, should be 1.684. So this is how you find critical values for T. And you will be given this table on the AP in class and everything like that. So that's how you find critical values. What we're going to do next is actually talk about how to find an interval. So just like with proportions, with means, it follows the same exact like format in terms of statistic plus or minus margin of error. So let's write up what those mean. So for means, it is X bar plus or minus T star. So let me fix that star. T star. There we go, which is the critical value for T times S of X over the square root of N. And S of X, remember, is sample standard deviation because we don't know the population one. The other thing that I want to highlight is the margin of error, which is this right here. Okay. So we're going to do two problems together. And right below that is just how to interpret